Grind is your best friend when you're doing C programming. It makes your life much easier. What Valgrind does is it runs your program through an emulated x86 CPU, and it tracks every single read and write from memory. Okay, so in computer systems you would have learnt about the load and store instructions and DLX, and they're the only instructions which transfer data from memory to registers or from registers to memory. Now, on x86, it doesn't have just load and store. There's lots of different instructions that can read and write from memory. But you don't need to worry about that at this point. All you need to know is that whenever your program accesses memory, either for reading or writing, if you're running it through Valgrind, Valgrind will actually keep track of all your memory accesses, and it will tell you as soon as you do one that's invalid. So, now, in order to do that, Valgrind runs your program through emulation, and because of all the extra checks it does, your program runs at least an order of magnitude slower than what it does normally. So you wouldn't normally use Valgrind all the time for testing your program. You would only use it if you want to specifically debug your program. So if you're getting crashes, then it's good to use Valgrind to check it. Or if you think your program is working fine, maybe run it through once or twice with Valgrind and see if that picks up any problems. But it does run it a lot slower. But this is only a fairly simple program, so we won't notice much of the difference. So the way that you run Valgrind is you say Valgrind, and then you run the command as normal. So I'll say Valgrind compare path 1, path 2. Okay, so this will print out a whole bunch of extra output. The thing with the double equals and the process ID here, that is the output that is produced by Valgrind. Now if we scroll up, we'll be able to see the error. So this has said invalid write of size 4, which has occurred on line 42 of compare.c. So let's go back to compare.c. Okay, so we can see that this is where the invalid write has occurred. So GDB was not picking it up at this point. It picked it up earlier when we had a null pointer, because it's very easy to tell that an attempt to write to a null pointer is invalid. However, this problem is a bit more subtle because we've freed that memory, but those addresses are still available. Okay, they're still in memory, so we can still write to them. It's just that we'll end up writing over something that we shouldn't be overwriting. So it's detected. So it keeps track of, whenever you call malloc and free, it records the fact that those addresses in memory are allocated or unallocated. And when we've called free, Valgrind has recorded the fact that that particular range of addresses is no longer available to us, so we should not be using it. And then, because it tracks every memory access, when it gets to this point and it tries to write to that location, Valgrind says, whoa, hang on, that's not in my set of available addresses that the program should be allowed to write to. So I know that that's an invalid write. Now, here's the cool part. Valgrind knows that we used to have that memory allocated and then we'd freed it. Okay, so it can tell us that the mistake we're making is we're trying to write inside a block of memory that we had previously freed. And, even better than that, it tells us where we freed it. So it says compare.c line 32, Alt G and Emacs at line 32. Right, so we can see that we freed the memory here, and then we tried to access it or write to it down here. Okay, reading from it would also be invalid. So from that we can tell, well, the mistake that we've made is actually freeing the entries up here because we still need them down here. Okay? So this makes it much easier to identify that problem. And similarly, it's found a similar error. We've tried to call realloc in get sorted entries, line 39, which is here. We've called realloc on start entries, but start entries has already been freed. And again, we can see the location that was freed. So this has picked up both of those errors. And then later on, we're getting a 6seg-v, and that's because we've got memory corruption that's happening earlier on. Okay, so Another thing you can do with valgrind is, so now potentially you could have a very large number of errors coming. I've seen programs where you have hundreds of different error messages print out. So in order to make this simpler, what we can do is we can actually step into the debugger as soon as the first error occurs. So when we get to this part, this will go into the debugger, and then we can continue as normal as what we've been doing with GDB, and we can look at different variables and things like that. So the way that you do that is you run valgrind, and you run --db attach equals yes, and then the rest of the command. So what that says to valgrind is, as soon as you notice the first error, take us into the debugger. So let's do that now. Okay, so it's detected the error, and it said, do you want to go into the debugger? So I will say yes. Okay, so now we're in the debugger. We can see the line of code that we're on. We can do a backtrace. We can print out different values and everything like that. And you can use all the commands I showed you before with GDB. Incidentally, in GDB, if you type help, that will give you a list of commands. And you can type help internals or help breakpoints, and that will show you even more commands that you can run. Okay, so suppose I've done my GDB stuff here, I've figured out what the problem is, I can say quit, and then this will continue running. I'll just say cancel there. That will finish running the program. And so I've tracked down my problem to here, and I'll fix that, and now I'll compile and run it through valgrind again. So it's a good idea, when you think your program is finished and you've tested it and it looks fine, it's a good idea to run it through valgrind again one more time before you submit it, or release it to the customer, just to see if there's any mistakes you've made that aren't showing up, because it's possible to have these lingering bugs in your program that don't show up most of the time, but they might show up a few months or a few years down the track when a customer is using your program. And that's not very nice to happen. So if you run valgrind again, now this will run through completely, and we'll see that valgrind has not reported any errors. Okay, now just because valgrind didn't report any errors there, that didn't mean my program is bug-free. I could still have buffer overflow vulnerabilities and things like that. But at least it showed me that when I ran it with those particular inputs, it didn't have any invalid memory accesses. Now, one more thing you need to know about is how to track down memory leaks. So in C, whenever you allocate memory, you have to explicitly free it when you're finished with it. So that's different to languages like Java and Python, which have garbage collection. Java and Python will keep track of what objects you still have references to, and when you drop the last reference, like when you don't have any variable for pointing to that object anymore, it will automatically figure out that it can free that. Okay? So that's called garbage collection. C does not have garbage collection. You're responsible for freeing memory yourself. And you can see down here where I've done that. I've got these calls to free. So I loop through the array and I free its contents. Now, if you forget to free memory that you've allocated, then that is called a memory leak. And it's not going to cause too many problems if your program only runs for a very short period of time. But suppose you've got a program which is running over a long period of time. For example, a web server or a file system that is running as part of an operating system kernel. In that situation, even if you have very small memory leaks, over time they can add up, and eventually you'll run out of memory and the program will crash. So in all cases, you should try and make sure that you don't have any memory leaks in your program. So what I'm going to do is I'm going to comment out these two lines of code which free this memory. And when I run this through valgrind, I can actually use valgrind to check, have I freed all the memory that I've allocated? So when I run this, it will not free that memory, and valgrind will report that to me at the end. So I'll recompile my program, Now, of course, that's given me a warning about unused variable I, because I commented out the code that used I. Not really a problem, but I'll just comment it out I just for completeness, so we're compiling without warnings. Okay. So now I'm going to run Valgrind with the memory leak detection enabled. So now, by the way, if you type Valgrind -- help, that will print out a whole bunch of command line options, so you can see what all of the options are there. And as you can see, there's quite a lot of them. The one that I'm interested in is this leak check option. So I want to say leak check equals full, and then my command. Okay, now at the end you'll see that it's got a summary of the leaks, and we lost about 15.5K worth of memory. Right? It doesn't sound like a lot, but if we were doing this stuff repeatedly millions of times in a long-running process like a file system, then that could cause some real problems when we eventually run out of memory. So Valgrind shows us all of the places where we've lost memory, and in this particular case it's all from the same place, but these are just different instances of when it's called that function that hasn't freed memory. So now the thing to remember is Valgrind doesn't know where you should free your memory, okay, because it can't figure out when you finished with it. So just because you've got a memory leak that's identified by Valgrind, that doesn't mean that you know the answer, that you can just automatically know where to put free in. You have to figure out at what point in your program that memory is not needed anymore and put the free in. But what Valgrind will tell you is where the memory was allocated. So in this particular case, the memory was allocated by malloc, which memory always is in the heap, and malloc was called by strdupe. Now, we're not really interested in strdupe, we didn't write that, that's part of the C library. The top function that we called here was compare.c, and it shows up the line number. So compare.c, line 38, is where we allocated the memory that we forgot to free. And you'll see that that's the same for all of these other lost records here, because in this particular case, there's only one instance, there's only one place in the program where we leak memory. But you may have multiple different locations where you've allocated memory but not free. So compare.c line 38, go back to the again, Alt-G, Alt-G, and we can see that this is where the memory was allocated in this call to strdupe. strdupe creates a newly allocated copy of the string. And in this particular case, strdupe, the result of that is what we were putting in the entries array. And that's what I commented about here, where I'm not freeing those entries in the array. Okay? So this won't tell us where to put the free, but it will tell us where we allocated the memory that we lost. And hopefully, given that information, you'll be able to figure out where you need to actually free the memory. So I'm going to now fix that bug by uncommenting these lines of code. And now I'll go back and I will recompile my program and run it through Valgrind again. And at the end here, it said all heap blocks were freed, no leaks are possible. Okay, so that's something that we should be happy about. Now, keep in mind, as before with the invalid memory accesses, just because your program doesn't leak memory when you test it, that doesn't mean that it's impossible for your program to leak altogether. There could be some situations which you didn't think to test in which it does leak memory, and it just so happened that these cases you tested with didn't bring up the memory leaks.